Good morning, students. Let us start the class. I am coming to the last part of the cyclic codes. How can you have a general form of decoder for cyclic codes at the receiver? That we are going to see now. So you can see here we have a particular block diagram. Let me slightly zoom out. Yeah, now you can see the complete block diagram, where you can see there are two XOR gates at the top and there is a feedback connections, and then we have a syndrome register. Later on we have error pattern detector. Below we have a buffer register. What happens at the receiver is, when the received vector is coming, initially S in will be closed and S out will be open. The switch S in will be closed and the switch S out will be open, and at that time the received vector is input to the buffer register and it is input through this XOR gate to the syndrome register as well. Now this error pattern detector is basically a combinational circuit, and in this error pattern detector it is going to check always one bit error, that too at the MSB. Now let us say at the MSB there is an error and that will be corrected immediately by the error pattern detector, and we are assuming right now only one bit error detection, one bit error correction. So that particular MSB, if it has an error, later on after all the 7 bits are input, now that S in will be closed and S out will be, S in will be opened and S out will be closed. At that time the corrected code is going to be coming out of the error pattern detector as well. That is the error correction is happening. If at all the MSB is not having an error, then gradually the syndrome register is basically a shift register. It will be shifted, the bits will be shifted to the right side, and at that time again the same error pattern detector is going to detect the error, and if there is error it is going to correct the error, and it will go on. Let us say now also if there is no error, one more bit shifting will happen, and this way it will go on until the complete length of the received vector is completed, and after which S in will be closed and S out will be open, and the corrected code will be output. That is how this is a general form of decoder at the receiver. And let us say there is a syndrome for which there cannot be any error correction, then only it will be detected, it will not be corrected. That thing we have already seen earlier, that the particular systems can have more number of error detection ability, but they will not be having the error correction ability if the particular position is not actually found out. So whatever I have told now, there is a brief explanation here. The pattern detector is a combinational logic circuit. The error pattern detector is a combination logic circuit which will output 1 if the bit position at x power n minus 1 is at error for a corresponding syndrome with the correctable error pattern. If there is no error at the MSB position, the error pattern detector will output 0. Now, whenever output 1 is obtained, that particular bit is corrected at once. When the output is 0, the bits are going to be shifted. Now, this procedure can be summarized as follows. Let me zoom in. The procedure can be summarized as follows. Initially, S in is closed and S out is open. You will have to visualize that block diagram again now. Initially, S in is closed and S out is open. Now, the received vector is shifted into the buffer register and the syndrome register. Now, S in is switched open and the output of the error pattern detector is checked for 1 or 0. After correction of the bit in the buffer register, S out is closed and the first received bit is shifted out of the buffer. At the same time, the syndrome register's contents are shifted right by 1 position. If the earlier output was 0, then it means that the error exists in the previous bits, hence the new syndrome is now verified for the detection of error. The procedure is repeated by shifting bit by bit until the entire received vector is shifted out of the buffer. At the end, the syndrome register will contain all zeros. Otherwise, it is an uncorrectable error pattern. If the syndrome register contains all zeros, means the complete received code vector is either having no errors or error was corrected. Now, if the syndrome register does not contain all zeros, then it means it is an uncorrectable error pattern. By the way, yesterday I had asked the question, has anybody found out why that 100 is a magical bit stream while we are correcting the errors in the cyclic codes? If anybody has found out, either you can unmute and tell me, or you can put it in the chat box. I will wait for the answer. Now we have come to the end of cyclic codes. Let me summarize whatever we had discussed till now. Okay, the summary. Yeah, Kuldeep is putting an answer. Sir, it is the first row of Hamming matrix. Okay, this is Kuldeep's answer. It is the first row of Hamming matrix. Is it so? Let us see. We have the Hamming transpose here. So it is the first row of Hamming matrix, that is part of the identity matrix. Then later if we give clock pulse, we get the entire Hamming matrix, right? So Kuldeep has found the answer. If we give the clock pulse, we get the entire Hamming matrix one by one. So it is basically this particular row which we are going to get again when we keep on proceeding with that inputting the additional clock pulses. Okay, so that is the answer. Anyway, congratulations Kuldeep that you have told me the answer. Let me proceed now. So finally I am summarizing the discussion of the cyclic codes. There are some points which I have mentioned here. I am trying to pull in this particular window. Okay. A brief summary. G of x has to be a factor of x power n plus 1 and g of x has to be of degree n minus k. We have seen this. And g of x is also a factor of all the valid code polynomials. This is important. G of x is also a factor of all the valid code polynomials. Because of this property only, we could actually easily construct the required matrices. Now the third property, non-systematic code vectors are obtained by multiplication. That means v of x is given as d of x into g of x. We had seen the examples earlier. Systematic code vectors are obtained as c of x equals r of x abridged with d of x, either abridging or concatenation using a pipe symbol. So c of x equals r of x abridged with d of x, where r of x is the remainder polynomial that is obtained by dividing x power n minus k into d of x by g of x. That is how systematic code vectors are obtained by polynomial division. Now the syndrome s of x has to be obtained as the remainder polynomial when the received vector z of x is divided by g of x. At the receiver, we will have to obtain the syndrome. For obtaining the syndrome, we perform the division once again. Now we have a notation for the received vector as z of x, and that has to be divided by the same generator polynomial g of x. Now the syndrome s of x has to be expressed in the degree n minus k minus 1 when it is expressed in bits. Now the last 2 points, the seventh point, G generator matrix is written in the form P abridged with IK, and Hamming matrix is written in the form In minus K abridged with P transposed. So these are the total summarized points for the cyclic codes. Now there are these additional exercises. You have to go through the notes for all these additional exercises. Right now I will not go through these additional exercises. Let me complete the portions, after which I will be having revision classes. In all the revision classes, I am going to discuss all the additional exercises of all the modules wherever I have put them. So let me skip these additional exercises for the time being. Now let me come to the last part of module 5. That is cyclic and convolutional codes. Just a minute, I am trying to pull this window out. Yeah. Okay. Now we are coming to the last part, that is cyclic and convolutional codes. Till now we have been seeing check bits along with message bits. Until now, whether it was a block code or whether it was a cyclic code, we had a relationship between the message bits and the check bits. Always we used to mention it as n comma k, where n is the total number of bits in the particular code vector and k is the number of bits in the data vector. So naturally n minus k used to be the number of check bits. But now we are not going to follow the same strategy later on for our newer applications. There is something called CRC, cyclic redundancy check. Now this is a regular application. Whenever you play a DVD also, there is a CRC going to happen. Normally whenever there is a digital transmission, there is a CRC going to happen. Cyclic redundancy check is going to happen. Let me explain it a little now. CRC is an error detecting code commonly used in digital networks and storage devices to detect errors in raw data. In general, this is going to happen even when you connect a pen drive to your laptop, or at times even from the hard disks to the main memory. When the data transfer is happening, there are errors possible, right? When you connect your pen drive or USB drive to the laptop also, there are errors possible because of noises in the electrical supply. So generally that error detection and correction should happen even with these. At least if error detection happens, then ARQ can be utilized again for transmitting the data. Anyhow, these are all serial communication devices. So even with the hard disk, even with the pen drive, there is this CRC working. Even with the DVD player, this CRC is working. Now, CRC is an error detecting code commonly used in digital networks and storage devices to detect errors in raw data. In this method, the blocks of data get a short check value attached at the end. These check bits are based on the remainder of the polynomial division of the block content, and the number of check bits is not related to the number of block bits as such. You can understand? Let me annotate this. See, in this method, the blocks of data get a short check value attached at the end. That means when the raw data is being transmitted, at that instance itself, additional bits are attached to the data based on a particular polynomial, the generator polynomial. Now these check bits are based on the remainder of a polynomial division. Remainder of a polynomial division of the block contents. And the number of check bits is not related. You can see this. Number of check bits is not related to the number of block bits as such. Why? In a serial transmission, we deal with kbps and mbps and gbps, right? Now every day when I upload the class video to YouTube, that uploading happens within a few seconds, not even a minute. That complete 1 hour or not exactly 1 hour, about 45 minutes always. All this 45 minutes video recording of the class is going to be uploaded. When it is uploaded into the YouTube channel, that uploading happen so fast. That means it is not kilobits per second, it is megabits per second. It is basically a serial transmission only. From my laptop, the video is going to be uploaded through the wired channel or wireless channel. Now, right now it is through wired channel only. So through the wired channel, when it is uploaded into the YouTube server, it is basically serial communication, but it is megabits per second. When the data transmission is happening at megabits per second, even at the other side, at the YouTube server, it has to perform error detection and correction there. Because in between my laptop and the YouTube server, there can be error. Because in between my laptop and the YouTube server, there is this channel. It can be wired channel, it can be wireless channel. There are so many routers, switches, servers in between, and there are multiple protocols in between. It is actually a OSI layer working in between me and YouTube. I hope you understand the OSI layer, or I think I have told you or not. There are 7 layers: physical, data link, network, transport, session, presentation, application. These are the 7 layers. At the bottommost layer, it is the hardware or it is the physical layer where actual electrical signals are going. Otherwise, on the top level, this is called OSI model, Open System Interconnect model, for any particular computerized system. Nowadays, technology means it is computerized system. So in this computerized system, we have 7 layers: physical, data link, network, transport, session, presentation, application. Now those who are undergoing the Cisco course, you know more about it. Now, how to remember these 7 layers? There is a basic acronym or basic sentence through which it can be easily remembered. All people seem to need data processing. All people seem to need data processing. So, all the 7 layers names can be remembered that way by the first alphabet of each word in this sentence. All people seem to need data processing. Now, why am I telling all these things to you is, between me and YouTube now, between my laptop and YouTube, there are these multiple layers working. The upper layers are working in my laptop and at YouTube, at YouTube server. But otherwise, there are many lower layers. So when the lower layers are there, physically it is a channel that is between me and YouTube. But there are other layers in the intermediate equipments. There are switches, there are routers. There is a big networking service between my laptop and the YouTube channel. So there are lot of other protocols being used. So when megabits of data is being transmitted in a serial fashion, now if at all we go for the systematic error detection and correction, where if we establish a relationship between the number of check bits and the number of data bits, there will be a lot of time wasted during this process itself. Lot of resources are going to be utilized. So it depends on the type of application. In all the applications, we need not really go for block coding, cyclic coding concept of relationship between check bits and the data bits. Now, in this particular check called CRC, cyclic redundancy check, the check bits are not related to the message bits in a mathematical fashion. They are obtained in a different way, in a different style. I am going to tell you that now. So, these check bits are based on the remainder of the polynomial division of the block contents, and the number of check bits is not related to the number of block bits as such. If it gets related, then the number of check bits also will be large in number, and unnecessarily a lot of resources are going to be wasted at that time. So, again, as I told you, it depends on the particular application. And now let me discuss further. The procedure is as follows. The polynomial is indicated as a binary number of m bits. Now this is called as key. I am going to show you later on the example. Now you can see I have put an example here. Let g of x equals 1 plus x cubed. Now this is the polynomial, generator polynomial which we are using. Now this can be represented as a binary number. Here x squared is missing, so we are writing it as 1 1 0 1. 1 is there, x squared is there, x cube is there. So we are writing the key accordingly is called 1101. Now this is called as key. The polynomial is indicated as a binary number of m bits, let us say. This is called as key. Now what happens is that the transmitter augment the block of data with the m-1 zeros at the end. You can see here I have an example. The block of data is 100100. This is the data now. Now the data is 6 bits. We will have to obtain the check bits now for this. So 100100 is the data. Now to this data augment, or we can say add at the end a block, augment the block of data with m-1 zeros. Now the key is 4 bits. We will have to add additional 3 zeros. You can see here 100100 is there as the data, additional 3 zeros are added. Let me annotate. So you can see this is the augmentation where additional 3 zeros. This 3 zeros is nothing but m-1. Here m is 4, right? You can see m is 4. The generator polynomial is expressed in the binary form. M is 4. So 4 minus 1 is 3 zeros have to be augmented. That is the first set. Just a minute. I am muting myself. Hello students, I am continuing. Sorry for the interruption in between. There was some small official work to be commenced. So let me continue now. We have this key 1101 which is 4 bits. Now we will have to add additional 3 zeros. m-1 is we are adding these 3 zeros. The block of data is 100100. We are adding 3 zeros. That is the first step. Augment the block of data with m-1 zeros at the end. Now perform mod 2 division of the block of data by the key. Again, I will have to mute myself. There is a small interruption. Let me complete it and come back to the class. Okay. Okay, my task is finished. Now there will be no more interruptions. Let me continue the class. So the first step is augment the block of data with the m-1 zeros at the end. The second step is perform modulo 2 division of the block of data by the key. Now we already are familiar with the modulo 2 division. I am going to show you the example anyhow. Finally, append the remainder at the end of the data and then transmit. Append the remainder. Now this remainder is going to be our check bits. Append the remainder at the end of the data. Data is 100100 only. Now for finding out that, we are doing these procedures and then transmit. Now at the receiver, perform modulo 2 division again. If r of x is 0, if the remainder is 0, then there is no error. Let us say if the remainder is non-zero, then again the receiver can go for a ARQ method of asking the transmitter to send the data once again. But in general, whenever a DVD is being played, or whenever the hard disk is being read, or whenever the USB is being read, the number of errors will be always much lesser. Why? Can anybody tell me? I am telling, whenever the DVD is being read, or when the hard disk is being read, or when the USB pen drive is being read, the number of errors will be lesser. Can anybody tell me why? Yes, right. Kuldeep is telling the answer. Channel is small. The transmitter as well as the receiver, they are at the vicinity. When they are at the vicinity, there are less number of errors. That is why we need not go for that systematic error detection and correction methodologies which we discussed till now. Otherwise, unnecessarily we are going to waste the resources. So we can easily go for the CRC check. Whenever you go for the CRC check, automatically what happens is, when the remainder is 0, there will be no error. So there is no need of ARQ now between receiver and transmitter. Whenever there is a non-zero remainder, only then the receiver will have some more time and it will ask the transmitter to send the previous data once again. Okay, that is the only delay that is going to happen in between transmitter and receiver. Otherwise, transmitter keeps on sending the data and receiver keeps on receiving the data. This is a useful application whenever we have a less chance of error in our data transmission. That's why I had told you that this CRC is useful in some applications where the channel is not going to introduce a lot of errors. So at the same time, CRC cannot be used for other applications which are critical applications where every time error detection and correction is required. For example, for satellite communication, definitely there is going to be error always. So in case of satellite communication, we cannot use CRC as such. That is the idea. So for satellite communication, we should have advanced error detection and correction methodologies which are based upon our previous discussions only. There are many advanced encoding and decoding methodologies. Actually, all those methodologies are beyond the scope of our syllabus for this undergrad course. For example, in your mobile phone itself, you have something called Viterbi encoder, Viterbi decoder, Reed-Solomon encoder, Viterbi decoder. There are such advanced coders and decoders. Of course, I am going to tell briefly about them at the end of this module. But we are not going to go into the deeper architectural details of such encoders and decoders. Cell phone contains a particular chip called vocoder. Vocoder means voice coder. Voice gets encoded into data. Later on, there are many algorithms applied along with the source encoding and channel encoding. And that is how, even when you speak through cell phone, again there is error detection and correction happening, but at a much larger speed. There we cannot go for CRC checking. Why? Because there is no ARQ possible between receiver and transmitter. Only thing is, when you and me are communicating through the mobile phone, if you are unable to listen to my speech properly, you can ask me to tell once again and I can tell once again. But that is between two human beings. But between machines, there is no ARQ possible. That is because It's a real-time data transmission. When there's a real-time data transmission, it is actually data streaming continuously. ARQ protocol cannot be used between receiver and transmitter. That is why advanced codex means coders and decoders. Advanced codecs have to be utilized in the advanced communication applications. But they are based on whatever fundamental concept we have discussed till now in this course. So let me show you the example now. Example, let g of x is 1 plus x cubed. I have already told you the key is 1101. Let block of data be 100100. As m equals 4, the block of data has to be augmented with 3 zeros at the end. Now let us perform modulo 2 division. We have added these 3 zeros at the end. Let me highlight this 0 0 0. Now let us keep on performing the modulo 2 division. Our key is 1101. So first let us put 1, this one, 1101. And now remember that in modulo 2 division, subtraction and addition are one and the same. 1 plus 1 is also going to be 0, 1 minus 1 is also going to be 0 anyhow. That is, we are going for modulo 2. So here 1 minus 1 anyhow it is going to be 0, otherwise also, and 0 XOR 1 now. This is basically XOR operation. So 0 minus 1 in the modulo 2, that is going to be 1, then 0 0 0, 1 1 is 0. Now take this particular 0 here, it became 1 0 0 0. Again put one more 1 here, and again 1 1 0 1, and again 1 1 is 0, 0 1 is 1, 0 0 is 0, 0 1 is 1. Now we take one more 0. We are taking this 0 1 by 1, take this 0, again keep on performing this way, and finally after the last 0 here, we have the remainder 0 0 1. This 1 1 is 0, 1 1 is 0, 0 0 is 0, last one is 0 and 1, modulo 2 operation results with 1. So at the end we have this 0 0 1. Now the encoded data is 100 100, last remainder is 001. At the receiver, this data is divided by the key. Let me show you the receiver later on. Now my question is, should remainder not be 0001? Why are we taking the remainder as 001? Can anybody tell me? When we perform the last modulo 2 operation, the remainder has to be 0001, right? Why have I written 001 only? Can anybody tell me? The reason has been already told. Yes, the reason is, as Kuldeep has told, 3 bits must be added to the block code. We had already taken m minus 1 there, right? From the generator polynomial, we had taken 4 bits of the key, and the algorithm which we used here is m minus 1. So we had augmented 3 zeros. Naturally, we will take only 3 bits of remainder, not 4 bits. That is the point here. Now therefore the encoded data is 100 100 and add the 001. Now you can see for 6 bits of data we have 3 bits of check bits, and the 6 and 3 are not related. It is not like our earlier case of n comma k. This total n here is now 9. Total n here is 9, but k here is 3. But n and k are unrelated. As I have told you, if we establish a relationship between them, then our work will be much larger, which is actually not required when the transmitter and receiver are at the vicinity itself. So this is the encoded data now. Now at the receiver, this data is divided by the key again. Now the ingenuity of the scheme is the choice of the key itself, right? It is based on the choice of the key, or by the choice of the generator polynomial. We are going to decide upon the number of bits in the remainder. So at the receiver now what happens? The received data is 100, 100, 001. Now again use the same key which was used at the transmitter, perform the division operations. Now first one is 11101, and here 11 is 0, 01 is 1, 000, 11 is 0. Take the next 0. Keep on taking those 3 bits only here. Instead of the 4 bits, keep on taking those 3 bits only here, and keep on taking the next bit from the divisor or dividend, whatever we call divisor and dividend. Inside one which we call, I don't know, I don't recall exactly. Maybe this is called divisor, this is called dividend. Anyway, or it can be the reverse also. So this way we perform the division. Now at the end you can see the remainder is 0000. This is at the receiver. As the remainder is now 0, there is no error in the received data. Let us say if there is a error. For example, let us say the data became 100000001. Now in the fourth position, if there is error, let us perform the division once again. Now the division results 100000001. That means at the fourth bit there is no error, as I have shown you. At the fourth bit now there is one error. So let us perform 1101 is now the dividend, and 100000001 is the divisor. Performing the same modulo 2 division, 11 is 0, 01 is 1, 00 is 0, 01 is 1. Take the 3 bits only, m minus 1 bits. Take the next bit 0. Proceeding this way, we come to the last remainder, that is 011. We were supposed to get 000. Instead we are getting 011. At the top side I have shown you 4 zeros. Actually the very first one we always discard. Even though I have shown you 4 zeros, as I have been telling you, the first one we discard. The last 3 are anyhow 000. That means there is no error. Now in this case you can see it is 011. That means the remainder is non-zero. Now as the remainder is non-zero, error needs to be detected and error needs to be corrected. One easy method is the receiver will ask the transmitter to send the data once again. That is easy method. Let us say otherwise, if the CRC is used with other types of applications, there just like the CRC, there are additional complicated methodologies to detect the error, where exactly the error happened, and to correct the error. And these complicated methodologies are based on, again, generator polynomials, multiplication division algorithms. This we had already discussed earlier. So now there is error needs to be detected and corrected, but now the procedure has to be slightly altered compared to the procedure which we discussed earlier. The generator polynomial which we have 1 plus x cubed, but we had gone for a different type of check bits. So the procedure need to be altered, and that alteration in procedure is actually more complicated, and that is when we are not discussing it here in our course, as I have been telling you. So these are the basics of CRC, cyclic redundancy check, which is quite a simple procedure. Except for the procedures of error detection and correction, we have discussed the basic scheme of CRC, and it is always used in our regular life as such now, as I have told you the applications. Let me proceed now for the last part of our module 5, that is called convolutional coding. We had seen block coding, we had seen cyclic coding. Now we are coming to a method called convolutional coding. In applications such as wireless communication and satellite communication, the block length can run up to thousands of bits, and the block length can be variable as well. Please understand this sentence. In the applications such as wireless communication and satellite communication, the block length can run up to thousands of bits. It is not like we are sending 6 bits or 7 bits or 8 bits at a time. You will learn more about it in future when you learn about packet switching, where a packet will contain a header information, it will contain a trailing information, it will contain the check bits there, it will contain the data bits there. Each packet is defined that way. So you are going to learn about it anyhow in detail, or you might have already learned about it in the Cisco course. Fine. Now the block length can run up to thousands of bits, and the block lengths need not be fixed. They can be variable depending upon the traffic. In general, algorithms can dynamically change from day-to-day application or between peak hour and non-peak hour applications. For example, always morning 9 to 11 is considered as peak hour in India as such, or in general in the whole earth. And again, evening 7 to 9 is considered as the peak hour, because people work a lot in the early morning when they send a lot of mails through internet, and they have a lot of interactions among the departments. So generally morning 9 to 11 is the peak hour as far as the data communication is concerned. Similarly, evening 7 to 9, when people are at home, again they'll keep on making calls to each other. They will use the communication resources that way. So in those peak hours, there has to be a different algorithm which is utilized by the communication setup. In the non-peak hours, there need not be the same algorithm used. For example, you can also see this in Bengaluru city when the BMTC buses are plying. During the peak hours only, there will be a large number of buses which are moving on the roads, because there will be more people traveling at that time. But during the non-peak hours, same number of buses need not be released from the BMTC bus stops or from the main bus stations, because at that time, if at all same number of buses are plying, then many buses will be moving empty. So there can be a dynamic change in algorithm depending upon the peak hour traffic and the non-peak hour traffic. Same thing is applicable here also in the data communication. Now even in the restaurants and in the hotels, they know when is the peak time for the customer's arrival and when is the non-peak time. Generally evening 7 to 9 is the peak time for almost all the restaurants, and that is when they will make themselves ready with all types of items also, because they know that that is the time where majority of customers are going to visit the restaurant. Otherwise, in general during daytime there will not be that much of traffic, except for the restaurants supplying breakfast and lunch. During breakfast time in the morning or during lunch time, maybe during 12 to 2, they will expect large amount of people at the restaurant. So accordingly they will prepare themselves, or accordingly they will prepare the items also. Why I am telling all these examples is, block lengths can be variable even in data communication. That means based on the peak hours and non-peak hours, there can be different dynamic algorithms utilized by the communication resources. So the first challenge is block lengths can run up to thousands of bits. Second challenge is block lengths are variable. Till now whatever we have discussed, we did not think about such complicated applications. But now wireless communication and SATCOM are complicated applications. That is when we use a method called convolutional coding. That is advantageous for such applications. Now this method does not transmit the data bits. It sends only the parity bits or the check bits on the channel. However, the trade-off of this method is that the decoding process becomes slower at the receiver, because we are sending only the parity bits or the check bits. At the receiver, the block decoder takes hard decisions based on the algorithms used, whereas the convolutional decoder takes soft decisions such as maximum likelihood. Today it is already time. Let me not go into the discussion of these details. I have told you the basics of convolutional coding now. We are not going to send the data bits, we are going to send only the parity bits or check bits. How it is exactly going to work out, we will see in the next class. Until then, take care and goodbye.